All right, hi everyone. I can see we've just about gone live just then. Let's double check. Can someone confirm if they can hear me? I know we don't have many people online right now, but if someone could confirm, that would be great. Maybe I'll just test myself. Give me one moment. Cool. It looks like the audio is perfect, so we might get started now. So yeah, welcome everyone to our Math 2018-2019 workshop. This is the first part of our two parts. Our second part will be tomorrow from 12 to 2 p.m. And yeah, we'll get straight into it. What we're going to be doing is we're going to be revising most of the major topics. So for today, this is what we have set to cover. So we'll be doing functions of several variables, extreme values, some vector calculus, some line integrals and that kind of stuff, and also some linear algebra. And next time, so tomorrow from 12 to 2 p.m., you guys will be doing differential equations. And yeah, you'll have a lot of fun doing both of those, I'm sure. Okay. Without further ado, I'll just get straight into it because we've got a lot of fun stuff to cover today. Okay, cool. So we're going to start off with a relatively simple question about partial derivatives. So we've got this function fxy, and we've seen functions before with single variables. So hopefully by now we're kind of familiar with how this works with like two variables. And basically the question is it an increasing or a decreasing function in the x direction? And when we think about increasing or decreasing in the x direction, what we're basically thinking about is partial derivatives. So if you do a derivative with respect to x. And the process we do this with, we'll need this a lot in our seminar today, so we will just go through it very briefly. Yeah, what we do is we just treat everything other than x as a constant. So like we've differentiated x squared before. It's not too bad. We just turn it into 2x. Right, and y cubed is just a constant, so no need to worry about that. Basically, when we're differentiating with respect to x, we just do this. Do 2x, and y cubed is just a constant there, so it's all good. Same thing here, like sine x. All we have to do is just treat this as a constant. Whenever we differentiate, we can just basically ignore the constant. So all that happens is we change this to 4e to the 4x, because that's the derivative of e to the 4x, and then we multiply by sine x, sine y. Right, so hopefully we're okay with that. Just treat all the y's as a constant. So if it helps you, you can just say, what if this were just 2? Right, sine 2 we would just ignore, it's just a constant. So that's where we are here. Cool, and so the next thing we want to do is it's asking us if it's increasing or decreasing at a certain point. And that basically means we need to sub in these specific values of x and y. So yeah, we've got this nice formula. Just chuck in the values, right? So chucked in the values, we get 2 times 0 times pi on 2 cubed. Well, it doesn't really matter, this is all 0. And then we plus 4 times e to the 4 times 0 times sine pi on 2. Right, so yeah, it looks like a confusing question, but it's really just about evaluating these partial derivatives, and we end up getting 4. And it has the same interpretation as a single variable derivative, right? If it's positive, it's increasing. So hopefully that was a nice question. If you have any questions about that, just let me know. But yeah, that's our first question. It's a nice one to warm up with, just about derivatives. Cool. Yeah, so our next question is a bit more involved. It's about the multivariate chain rule, and it looks a bit more complicated, but it's not too much different. But basically, we're given u as a function of x and y. The trouble is, though, x and y, they're both defined in terms of other variables. And this is kind of like our chain rule, right? Functions of a function. And just like we have a chain rule in the first with one variable, we have a chain rule with multiple variables. Right, so we've got u equals x squared plus 4y, and both of these depend on two other variables, s and t. Right, so to find the rates of change, exactly as I just said, we need to use a chain rule. Okay, So this is a chain rule. It looks a bit confusing at first, but it actually makes perfect sense if we think about it. Because what we're trying to do is we're trying to find out how this thing changes as, let's just focus on this first one. We're trying to find out how this thing changes, and it's defined in terms of x and y. And then x and y, just like in this situation, they're both defined in terms of u and v. So what's going to happen is, if u changes, how will z change? Well, there are two sources of change. So number one, if u changes, then u can affect x, right? So that's why we have dx du. And then if u changes x, then x can also affect z. It's kind of like a flowchart, right? If z is a function of x and y, then, well, if u changes, it can either change x or it can change y. And that's why we have these two terms. So dx du times dz dx plus dy du, oopsies, times dz dy. Right, so it looks pretty complicated, but it's really just thinking about how z can change in terms of these two variables. You can just sum up these two products. And same thing with v. Sum up these two products. Right, first of all, how does z change as x changes? Multiply that by how x changes as v changes, then do the same thing with y. Okay, if that's a bit confusing, let's just do an example. Like we've got this exact example. So u is defined in terms of x and y. And then x is defined in terms of s and t. And so is y. So, well, let's just do a first example. Let's try to find du dt. Well, du dt has two components. Either x can change, right? X can change due to t. That's why we have du dx times dx dt. Or it can change due to y. All right, that's pretty good, right? Because now we all know we can just sub in these derivatives. So that's exactly what we've done over here. We've gotten du dx, and well, it's just partial derivatives, that turns into 2x. And we've also got du dy, that's a partial derivative, it turns into 4. Cool. So in other words, this turns into 2x, this turns into 4. Right? And so the next step, if you can guess, du dt, it's all about finding out how each of these things change as t changes. So that's our next step. And you can see we've just done the partial derivatives again. So 3st, differentiate with respect to t, we get 3s. 4s ln t, differentiate with respect to t, we get 4s on t. Okay, that's pretty good. And now we get a simplified version. But to tell you the truth, right, we're not actually done because the question's asking us to find the derivatives with respect to t and s. Right, and right now we've still got an x in there. That's not very ideal because we were trying to get everything in terms of t and s. And, well, there's actually a pretty simple solution. To finish this off, use our substitution, x equals 3st. Right, because that gives us x in terms of s and t. Because that's pretty good. So we just replace that. We're not actually done. Our answer needs to be in terms of t and s. And we end up getting this thing over here. So 6 times 3st times s plus 16s on t. And simplifying that out, we just get this function in terms of s and t. Cool. And so it's the exact same process with du ds. Basically, we start off with how fast it's changing with respect to each of these variables, x and y. So if you remember 2x and 4 from before, and then we just do the exact same thing except with t. So partial derivative there. Sorry, this except with s. Partial derivative there. Right, add them all together, we get this. And hopefully you're noticing that same problem we just saw. We still have an x in here. We don't really want an x in here. So just replace the x with 3st. And beautiful, we are there. Awesome, so just put it all together, and we'll get that du ds and du dt are given by these two formulae. Right, so hopefully that makes sense. Let me know if you have any questions about that. But for now, we'll move on to the next application, which is Taylor series. Cool. So yeah, just to give a bit of context, right, this is building on what we've done before. So if you want to do a function f around a single point a, this is called the Taylor series about a. You can kind of do a polynomial in terms of x minus a, right? And so each of these terms, we've seen this before. We start off with fa, then we have f prime a, f double prime a, and it keeps on going. It turns out we can have the same kind of thing for functions of two variables. Okay, so that might look a bit scary, but it's not too scary. because it's actually quite the same point, right? So the Taylor series is kind of doing it as a polynomial. And when we think about polynomials of two variables, right, we can have constant terms, obviously. So let's just say we have something like 3. We can also have the linear terms, so like x minus a plus y minus b. But now you notice instead of just one linear term, we have 2 linear terms, right? And another example would be second order terms. We have stuff like x minus a squared, we have y minus b squared, and we have x minus a, y minus b. And why are these the second order terms? Because the powers add up to 2. So what we've got over here is we've got the constant term, we've got the linear terms, and exactly the same thing as what I just said, right? The second order terms here. So x minus a squared, x minus a times y minus b, and y minus b squared. And it seems like the derivation, it's very simple for us to remember because all of the x's are associated with x derivatives. So we've got a y here, there's a y derivative, right? And x minus a squared, there's a second derivative with respect to x, right? And this thing over here, which has both of them, it's the mixed derivative, right? So they made it really simple for us to remember. The only thing to keep and be mindful of is this thing. So 1 on 2 factorial, because that's actually what we do with our normal Taylor series, right? We always have a 1 on 2 factorial next to the second order terms. Cool. And another thing to be mindful of is this 2 over here. You can kind of think of it as like when we expanded a sum of 2 squares, for example, we have x squared plus y squared, but then we have 2xy. There's going to be this 2 of the mixed terms. And that's kind of what we got here, right? So realistically, if you can just kind of understand this formula, all of these questions become pretty simple. Okay, Taylor series expansion of the function about the point 44. So right off the bat, if we write the polynomial, it's going to be equal to a constant term. So it's going to be f44 plus all the derivatives. So df dx 44. And then we can think about it, it's going to be x minus 4. Because remember, we put like terms with like things. Right, then we do the same thing, df dy, 44. And you guessed it, it's going to be y minus 4. And you keep on going, there's a nice way to remember this, right? Same as like first, like single variable functions, we've got 1 on 2 factorial. All of that times, we'll have the second derivative here. And hopefully you can remember that it's going to be x minus 4 squared. Then we'll have 2 times the mixed derivative. And then you'll have x minus 4, y minus 4. And then you'll have d squared f dy squared, y minus 4 all squared. Okay, so basically all we need to do is just put that together. And we won't go through the mechanics, but basically you can just see, before you even calculate the series, you can just calculate the constant term, sine 20. We do the same thing with all the first order derivatives. So how do we get this? Well, we just differentiated. And then we just evaluated that 4. You can see why we're not doing this all live. It would be a bit of a waste of time. But yeah, like just keep on going, and you'll see we have all the second order derivatives too. Cool. So yeah, like that's all our derivatives. Now just put it into one function. And yeah, that's what we've got over here. So all you do is you say, you can compile all your information. We've got the first derivative down here, that's cos 20, and we'll multiply that by x minus 4. Okay. Then we do the y derivative, 8 cos 20, multiply that by y minus 4. And we keep on going through all the second order terms. And you guessed it, we'll also need this 2 over here. So what do I mean by that? Like the mixed derivative is minus 8 sine 20. And we've got over here minus 16 sine 20. It's because of that 2 from before. So I'll just scroll up real quick. Yeah, this thing. So yeah, if you can get the hang of that, then you'll be perfect with these Taylor series questions. Cool. Yeah, well, we might skip through this error approximations, because we have a lot to do. I mean, if we have time at the end, we'll do it as well. But yeah, we'll skip through this, and we'll move on to the next thing, because error approximations is fairly straightforward. There's just a single formula to do. We'll spend our time on Leibniz's rule. Cool. Yeah, so we've got Leibniz's rule here, and it looks really scary again. A lot of things look kind of scary at first, But basically what we're saying is we've got a function. And well, let's say, for example, we have a normal derivative. We have a normal integral like t squared dt. Like that's a normal integral, right? We can calculate that pretty easily. I won't calculate it, there's not much point in that. But what is this saying? It's saying that this integral is in terms of t, but we have like x's lying around everywhere. So this thing is going to be a function of x and t. This integrand, so the integrand, depends on x. Same thing over here, these bounds, they've got to also depend on x. Right, so Leibniz's rule is just saying that if you've got an integral and the bounds in the integrand depend on a different variable, then this is how you differentiate that function. Yeah, so what this means is the sources of change in this integral, when x changes, we can break this down into 3 terms. First of all, well, let me think about it, right? This function, let's just say this function, we're integrating with respect to t from 1 to 2, for example. And then this function itself, it depends on x, right? If this function increases when x increases, then you can kind of see that the integral will always increase as x increases, right? So that's why we have this first term. The first thing we do is we move this inside, and basically we've got the integral of the derivative with respect to x. The next thing that we do is we say, okay, what happens if the bounds change? If this bound increases, then, well, the integral will also increase as well, right? So that's what this term is. Well, all you're doing over here is you're going from fxt to fx vx. And that just means you're subbing in t equals vx, right? So basically all you're doing is just subbing in this top bound into this formula. And then you multiply by the derivative of the top thing. And we do the exact same thing with the bottom, but the idea is that this has to be negative, because if this thing increases, if the bottom bound increases, then, well, our integral will increase, right? So that's why we have a negative here. We do minus the function when we sub in u times the derivative of u, okay? That might be kind of overwhelming, but just remember there are 3 things that can change the bounds. Sorry, there are 3 things that can change the top bound, the bottom bound, and the actual function inside. And that's the reason for these 3 terms. And what's really cool is if you have a special case of Leibniz's rule where this is just a constant, this is just a constant, then you can imagine that these 2 terms will disappear, and we're just left with just putting this derivative inside. Cool. Right, so hopefully that kind of makes sense, but an example will make it a bit clearer. Okay, so we're trying to differentiate this, and, well, why do we use Leibniz's rule? Because we're differentiating something with respect to x, where the bounds actually depend on x, right? And also the function inside depends on x. So, well, I'll just point this out. This is going to be fxy. This is going to be, which one was u and v? This is going to be vx. And this will be ux. Cool. All right, so first things first, let's apply it term by term. Okay, so the easiest one to remember is just kind of pushing the derivative inside. So we can just push this inside, and we'll get d on dx times 1 on y sine xy dy. Right, so that's pretty good. Derivative with respect to x of this. Okay, and that's our first thing. Right, we shouldn't be too happy because we still have stuff to do, but let's just go with this for now. That's our first term. Right, and oh, they've actually done it over here. Let's do it over here. It's not too bad. Differentiating this with respect to x, just treat y as a constant. This is just sine of x times a constant. So all you have to do is just change it to cos and multiply the constant on the outside. So I'll just make this pretty clear. This thing turns into that, right? Because we just differentiate with respect to x. Yeah, exactly this. And that's our first beautiful step. Cool. If we can remember the next step, basically what we do then is we say, okay, the next thing we do is what if this bound increases? And to do that, if you remember, you basically just sub in 2x to be equal to y. So we do 1 on 2x times, I should not obscure the question, 1 on 2x times sine x times 2x. And remember, we multiply by the derivative of this top thing, times 2. Then we do the same thing with the bottom. Actually, I'll just project it next. It's all good. We do the same thing with the bottom right, except we have a minus sign. we do a minus times subbing in y into x squared. And then we multiply by the derivative of the bottom. Right, so if you want to double check what that means, you can check Leibniz's rule again. Basically it just says sub this into your bounds. Sub this in. And then multiply by the derivative. Cool, and we'll just basically simplify all of this. It's not super interesting to do all these calculations, so I'll just skip through it. But you should get something like this. But the important part really is just knowing those three terms, right? In this case, we need all three terms because these aren't constant. Cool. All right, so this is a bit of a tougher question. We're using Leibniz's rule to evaluate this. But the good thing is they give us an integral first. Okay, so somehow, let's break this question down. We're given some information. Somehow we need to transform this integral into this second integral, right? Somehow transform a half into a 3/2, right? And when we think about that, right, what operation do we think we want to use there? Well, it sounds a bit like differentiation, right? And Leibniz's rule is all about differentiation. So if somehow we can push this inside, right, we can differentiate this and then somehow push it inside as Leibniz's rule says, then, well, this a half would probably change it to 3/2, right? Because we're decreasing the power. So that's kind of how we want to break these kinds of questions down, right? What are we trying to do? We'll change this half to a 3/2. So probably going to use Leibniz's rule. Yeah. So that explanation is down here. So we're effectively decreasing the power to which this thing is raised. And exactly, differentiation. Cool. So differentiate both sides with respect to x. So the simple part is just saying what does the right-hand side turn into? It's just a constant. So that turns into 0. Cool. The harder part and the part that involves Leibniz's rule is saying, okay, how do we actually change this into the form we want? So let's differentiate this. Okay, and hopefully we can see that in this case we're differentiating with respect to a. So what here depends on a? Remember there are three things: the thing inside the function, the top bound, and the lower bound. Right? So let's just see how those three change. And 0 doesn't change. Or actually, yeah, I'll just explain what these three terms are. Yeah, first of all, we've moved this derivative inside. Hopefully that part is okay. It's a bit easier to remember. We've got this first. The next thing we do is we say, remember, we say sub this into there. So sub a into x, and we've got this. And then we multiply by the derivative of the top part. And finally, this is 0. It's a constant, so this last term does not need to be here. Cool. All right, so we're looking pretty good so far. Yeah, let's continue. And we simplify a bit. Well, maybe I'll just do this as well because it's a bit more involved. But how would you change this first term? Well, just remember how partial differentiation works. Basically treat x as a constant. So we've got 1 on x squared plus a squared, 3/2, times minus 1/2. And then you multiply by the derivative of a squared, so times 2a. Right, and the awesome thing about this, right, is all of this is a constant with respect to x. So we can actually take this out. And that's what we'll do on the next slide. We've got minus a times this integral. And then what does this turn into? Well, basically we just subbed it in. We got 1 on root 2 times a. Okay. So basically what we've done is we've just tried to simplify this a bit. Because now we're trying to find this integral. Cool. And hopefully you can see we're kind of close because now all we have to do is find this thing. And remember, checking our other side, this thing was actually equal to 0, right? So if this thing is equal to 0, then, well, we can just solve for it like a linear equation, right? So we have a times this integral is equal to 1 on root 2 times a. And, well, just divide, and we get exactly what we need. Cool. Right, so hopefully that all made sense. If there are any questions whatsoever, just don't hesitate to shout in the chat. Yeah, that's basically how Leibniz's rule works, right? Don't get distracted by all of this confusion, right? Just think about what you need to do, which in this case is just differentiate, right? Differentiate this thing to turn it into 3/2, right? And then use Leibniz's rule. Cool. Awesome. So that's Leibniz's rule done. Those are the kinds of questions you get for them. You might be asked to find one integral in terms of another, and that's what we just did. All you have to do is just apply those three things. So remember the three sources of change. One is the function inside. We also have the top bound. And we also have the bottom bound. Cool. All right, time to move on to our second part, which is on extreme values. So extreme values are pretty cool because in univariate functions, we talked about max and min functions. And the way we did that was we found when the derivative is equal to 0. Turns out with multivariate functions, we can do the same thing, except we don't just have one derivative, right? We have multiple first order partial derivatives. And if you're not familiar with that term, basically it just means differentiating once. So df dx, df dy. If you do happen to have a third variable, then df dz. But yeah, basically those kinds of terms. So all of these now need to be equal to 0. And what that means is, generally speaking, you just need to solve a few simultaneous equations. Cool. Yeah, the other thing we can do is we can also classify these points. This is called classifying. So if you remember from maybe first year, maybe high school, in univariate functions, you can just use the second derivative, generally. It turns out there's an exact same formula with multivariate functions. But because we have so many types of derivatives, it's a bit more complicated. And here it is. So this expression, which you would have seen in your lecture notes, it's equal to basically a combination of different second derivatives. Right, so we've got the second derivative with respect to x. We've got the second with respect to y. And we've got the mixed one. Right, and just basically this expression tells us everything we need to know. Because we have these conditions. If it's greater than 0, then we actually have a turning point. If this thing is greater than 0, we have a local max or a local min. Right, and so what we do is once we know that, we check the sign of this first thing, and we say if it's negative, it's a max, and if it's positive, it's a min. That's pretty good. The other thing we know is that if it's negative, then it's a saddle point. So when we saw this diagram before, there was this thing called the saddle point. You can see it's neither a minimum nor a maximum, right? It goes down over here, it goes up there. And if this is less than 0, then that's what we've got, it's a saddle point. And finally, if it's equal to 0, then it's inconclusive, and we'll need to do something else, but you'll rarely get stuff like this. Okay, cool. So let's just try to apply this. We've got critical points. We've got a function, right? And we're trying to find the critical points. So finding the critical points, don't need this just yet, don't need this formula just yet. All we need to do is just solve for when the partial derivatives are equal to 0. So that's our partial derivative, and that's our y derivative. Cool. So it looks a bit overwhelming because we've got like 2 variables with 2 equations, but generally what you can do in these kinds of questions is you can either substitute or you can try to factorize stuff. In this case, we've got a really good opportunity to factorize. If 6x squared plus 6xy is equal to 0, then, well, that means that x squared plus xy is equal to 0. And, well, that's a nice factorization, right? x plus y equals 0. And the reason why we like that is because then we get a straight up solution for x and y, right? Either x equals 0 or x equals minus y. And once we've gotten that right, out of this first equation, we sub it into the second equation. So, yeah, factorize x plus y equals 0, and our 2 cases. So first of all, if you do x equals 0, then, well, you sub it into the second one, this disappears, and you get 2y minus 1 equals 0. Okay, so if 2y minus 1 equals 0, then y equals a half. So before you get like confused and start thinking about other stuff, just remember we've got 0, a half. That's our first point. Yeah, then we have our other option where x is equal to minus y. Then I said this briefly before, we try to substitute. So replace all the x's with minus y's. That way we're just left with an equation for y, and we can solve for that. And we get this. And yeah, we've got that over here, and we've taken the liberty of solving this equation for you, so we don't have to waste time factorizing. But now we've got y equals -1 and y equals a third are our two solutions. So it's really useful for this sort of stuff. Don't get confused. Just try to sum up your answer. Right, so our first point was 0.5. Our next point is, well, we've got y equals -1, and we've got x equals -y. That means x equals 1. And this final one is going to be equal to, well, y equals a third. Well, what about x? It's just going to be a minus a third. Right, so if it really helps you, try to write up these points as you go, just so it's a lot easier for you. But yeah, now that we've gotten these points, time for the fun. This is where the fun begins, right? Yeah, we want to calculate d. So second order derivatives, I won't go into the process of doing this, but just differentiate again. We've got 12x plus 6y, we've got 2, we've got 6x. So if you remember our formula, it was equal to these two multiplied together minus this last one squared. Right, so perfect. We've got 12x plus 6y times 2, which is that, minus 6x all squared. Okay, that's pretty good. And then all we have to do really is just sub this in to our 3 points. So this one's 0.5. Yeah, we've got d 0.5 equals 6, right? Just sub it in. In fact, maybe let's just sub it in just in case. We've got 24 times 0 plus 12 times a half minus 36 times 0 squared. And, well, this all disappears. We've just got 6. Awesome. Right, so that's greater than 0, which, if you recall, means we've got a local max or a local min. And then just to figure out which one, we check this one. Remember, this term alone is equal to 12x plus 6y, which is equal to 3. That's greater than 0, so we've got a local min. Awesome. And the next one, we do the exact same process. This time it's less than 0. Hopefully you remember that's a saddle point. This one too. This might be a typo, but it's a saddle point because it's going to be less than 0, I'm pretty sure. This one was meant to be less than 0. When the slides are uploaded after this workshop, we'll correct that. But yeah, for now, it's less than 0, so it's a saddle point. Cool. And the final thing is just double check the question, right? Because the question says, provide the function value at these critical points. So really all we need to do is just sub in our values of x and y, and then we're all good. Right, so at this point over here, at 0.5, we just sub it in, right? It's not too complicated. We get minus 1 on 4. This one we get minus 5 on 27. This one we get 1, okay? That's just like tying up our answer in a nice bow, answering the question. But yeah, the real gist of it is make sure you understand how to use this lovely thing, d, because d tells us everything we need to know. Cool. Yeah, there's this other type of critical point that we use with Lagrange multipliers. And the way you identify that you need to use a Lagrange multiplier is by actually checking, well, in this case, we've got a constraint. It's not just like maximize volume in general, it's like maximize volume under this constraint. Surface area is equal to 50. And that's what we call, as I just said, a constraint. So this is what we call a constrained optimization problem. And the maximum possible volume is like we're maximizing volume given this constraint. So, well, with these kinds of questions, yeah, we want to use what's called the method of Lagrange multipliers. We can't just use a simple unrestricted optimization problem. And there's a lovely little thing we have to know before we jump into that, the gradient. So I'm assuming we would have done this in first year. The idea is it's just the collection of all first order partial derivatives in order. So if we've got a function like f x, y, z, it's going to be equal to df dx, df dy, df dz. Sorry, this is it's an L-shaped vector, but you get the point, right? It's 3 components. I'll just draw it down here. Yeah, so that's our gradient. And we need to know this because Lagrange multipliers work based on gradient. So in this case, we need to convert everything to maths. So I know we saw stuff with like surface areas and volumes, but in general, when we want to use Lagrange multipliers, everything needs to be in terms of an equation. And that's how we like things in maths, right? So we have to say the critical values of a function. So this is the function that we're trying to maximize. F. And when we look at the constraint, this is the equation that defines the constraint. So I'll just write that up too. And once you've gotten those two equations, you can just calculate the gradients, solve this formula, and there's one extra thing you need. The constraint also needs to be satisfied. So in a way, you need, like, this is kind of n equations, because there are n components. And this is an extra equation. But just remember you need both of these to be solved, right? You can't maximize a function subject to a constraint if the constraint doesn't hold. This is really important. Okay, so yeah, we'll solve a set of simultaneous equations of n plus 1 variables. So we've got x1 to xn, and we've also got this lambda. And one extra note, in the case of Lagrange multipliers, we don't need to check the nature of the critical points. We can just find all of them, right? Just find every last one and just brute force it, right? Which one is the highest? That's the max. Which one is the lowest? That's the min. Cool. All right, so back to this. We've talked a bit about the process. Let's try to convert this all into maths, right? Because we can't exactly say our function is surface area. So let's just define our variables first. A cylinder has two variables. It has R and it has H. So here's there's a maths course, right? So let's convert all this information to maths. By the way, there's a bit of a typo. This should be 16 pi. And that will be corrected when the slides are uploaded. Yeah, 16 pi. So yeah, convert all this information to maths. So yeah, start off with the variables you need. So cylinder with base but no lid. That's going to have a radius and a height. Okay, so first of all, what's the constraint? The constraint is surface area, right? So let's calculate surface area. Well, it's got a base, so that's going to be pi r squared. It's got this, well, it needs to have the thing around the cylinder, otherwise it's not a cylinder. And that will be, because it's just draw it out. It's going to be equal to this length, so this length over here, times the height, right? So it's going to be, the length is going to be 2 pi r times the height h. And I would love to add this on the top, but it actually tells us the cylinder has no lid. Right, so basically this is our surface area. Right, so if our constraint is surface area equals 16 pi, then, well, what that means, right, is that our function g, remember g is the function such that the constraint is equal to 0. Our function g needs to be, let's write that out. Our function g needs to be, surface area is set to 16 pi. So it needs to be pi r squared plus 2 pi r h minus 16 pi. Okay. Hopefully that all makes sense because we're just trying to set the constraint to be something such that the function is equal to 0. That's our g. And what about volume? That's the function we're trying to maximize. Right, the volume is the function we're trying to maximize. So, well, what's the volume going to be? Well, it's going to be pi r squared, the base, times the height. So, yeah, that's basically f. And that's pretty awesome. Yeah, so we've got these two things. So a nice way to start off this question is just to look at the variables, try to define our functions, and convert to maths. Right, so now we have the function f, which we just talked about, and the function g. And now you can tell where we're all ready to go, or everything is in motion, because we just take the gradient then. And I won't go into calculating the gradient, but you can see we have to do it in the right order. So this has to be the partial derivative of f with respect to r, and this second one with respect to h. Yeah, and that's what we've done here. Same thing over here, we've done this. Okay, and what we do now is we say we need to solve such that the gradient of f is equal to lambda times the gradient of g. Cool. So after we solve this equation, we'll need to sub it back into our constraint. So we need to find some relationship between r and h that we can use, right? Because remember our constraint was where is our constraint? I'll write it up again. Our constraint is that pi r squared plus 2 pi r h is equal to 16 pi, right? So yeah, if you solve this equation, that's all well and good. But remember from before, we not only had this equation, but we also have to solve the constraint equation. So generally what we'll do, right, is we'll end up with some relationship between r and h, so like maybe r equals h. Then you can sub that in, and then you solve for r and h, right? So that's what we're going for here. Cool. So we'll start with this, and you might recall from before we did a lot of factorization, just because it's really cool to factorize things and makes things easier. So let's do exactly that. Let's factorize both of these equations. So, well, like very first thing, right, we don't like random pi's lying around, so let's just cut that out. Right, that's looking pretty good so far. So 2rh equals lambda times 2r plus 2h. I'd also prefer not to have random 2's lying around, so let's get rid of that. So let's do RH equals lambda times r plus h. Okay, that's pretty decent. Yeah, that's pretty good. And then we'll look at the second one. We'll get pi r squared equals lambda times 2 pi r. Well, first of all, we can get rid of the pi right off the bat. Yeah, that's pretty good. And be careful, because you can't just get rid of the r, because it could be that r is equal to 0. So you have to factorize this again. And what you end up with is r minus 2 lambda times r equals 0. Okay, that's pretty good. Yeah, so that's looking pretty good. And what that means is that now we have exactly what we had in that other question, right? We have two cases. Either r can be equal to 0, or r can be equal to 2 lambda. Okay. So yeah, we've got this over here, and you'll find with Lagrange multipliers, these kinds of edge cases where things are equal to 0, they're edge cases, and they're usually impossible. Because if r is equal to 0, right, what's our constraint? Our constraint is SA equals 16 pi. Well, the formula for SA is going to be, where was it? It was, I'll just write it up again, pi r squared plus 2 pi r h. Like, that's not possible to be equal to 16 pi if r is 0, because then all this all disappears. So we can just ignore it. Or you should write out that we can ignore it because it's impossible. But yeah, just ignore that one. And we know that the other one has to be true. R has to be equal to 2 lambda. Okay, so two cases. R is equal to 0, or this one is equal to 0. And it turns out that this is equal to 0. Okay, so we have a bit more clarity now. And what we'll usually do, our general strategy, is try to eliminate lambda from the equations. Right, why is that? Because we want to find a relationship between r and h. So relationship between r and h. Because then, like as I said before, right, you get this surface area equation. You can sub in that relationship, and then you can solve for one of the variables. Okay, so yeah, let's just try to find a relationship between r and h by eliminating lambda. And the best way to eliminate things, set them as a subject. This is just an example, by the way. Set them as a subject, then they're equal, right? These two things are equal. It's like these things are colliding, no one needs them anymore, and these are equal, right? So generally try to make lambda the subject, and then try to eliminate. Cool. And if you actually do the algebra, it's not that hard to show that lambda is equal to these two expressions, and then you just equate them, right? Get rid of lambda. No one likes lambda, right? So then we're left with RH on r plus h equals r on 2. And at this point, you can get rid of r, because we know that r is not equal to 0. So that means that I'll just solve it as well. H on r plus h equals 1 on 2, which means that 2h equals r plus h. And r equals h. Beautiful. So yeah, exactly what I said before, we sub it back into our constraint. Right, and then we can solve, there's just one variable left. Right, and then we solve for that. You can instantly see, get rid of the pi's, no one likes the pi's. 3h squared equals 16. So then h squared equals 16 on 3. And then we end up with h equals 4 on root 3. Awesome. So hopefully that all makes sense, right? We're just trying to solve for this, right? And the reason why we don't take the negative value is because we've got a length here. Cool. Yeah, exactly what we've got here. H equals 4 on root 3. And we only have one critical point to choose from, so what that means is no options. So just sub it in, that's our max volume. We get 2 pi. This is our volume formula, so from 2 pi from pi r squared times h. It actually turns into pi r cubed. Sorry, there should not be a 2 there. There should be a 64. But basically just sub it in and we get v equals 64 pi on 3 root 3. Cool. And that's our final equation. So the general gist is just to get rid of all these lambdas. Just try to find r and h in terms of each other. Then you can sub it into the constraint and solve. Sometimes you'll get more than one, and in that case, we do what I just said before. You do all of them, and you see which one is the highest, and which one is the lowest. Hooray. Okay, time to move on to the meatier part of this seminar, which is on vector calculus, and also we'll do some matrices stuff. Okay, so before we actually do any of the maths, we have to understand a few things. So what is a curve? Well, a curve is an equation like this. We've got 3 coordinates, and each of them is dependent upon a parameter t, and it changes as t changes. So, for example, maybe if t is equal to 0, we've got x, y, z equals 0, 0, 0. But then as t varies, it increases to 1. Maybe this curve moves around. It goes from 0, 0, 0, maybe it goes on a nice little trip around. Okay, I'll remove that. But basically the idea is that as t changes, this curve changes as well. And this might help us a little bit with trying to understand some of the harder questions. But basically a curve is just an equation that traces out coordinates. Another thing we need to know is a vector field. So a vector field, well, mathematically it's a function from r cubed to r cubed. So you take 3 variables, x, y, z, and you return 3 different functions. So f1, f2, f3. So we've given an example, right? We've got x squared, y squared, x sine z, because it takes these 3 variables, x, y, z, and it spits out 3 functions, right? And the physical interpretation of this on the diagram is just it takes a point, right? And it says, based on this point, we've got a nice vector, right? So based on this point, we've got this vector up there. Based on this point, we've got this vector up there. Doesn't matter. The point is that it maps r cubed to r cubed. Now that we know those 2 things, we can talk about line integrals. So a line integral is an integral, number 1, over a curve. Like we've done integrals over intervals, so you can integrate from here to here, you'll get an area. But now you can integrate over curves, which makes like a lot of sense, right? You can just integrate over there, right? And the other thing is it integrates a vector field. So number 1, we're integrating over a curve. Number 2, we're integrating a vector field. Okay, so how do we actually do this? Well, there's this nice little equation, but basically it comes down to a sum of 3 things. So recall that a vector field is like 3 functions. I will bring this example down just because it's useful to have an example. So f x, y, z equals x squared, y squared, x sine z. Okay, I'll bring it down and we have this nice little thing over here. But yeah, that's our vector field. And the 3 things we do is we sum up 3 things, okay? So first of all, this is f1, right? And what we do is we say, let's define this curve in terms of a parameter. So recall that a curve is like ct equals xt, yt, zt. Right, and what we say is that instead of integrating over this vague thing called a curve, we can integrate everything in terms of t. And we can say t varies over an interval, right? So t varies over ab. So if this t varies over ab, we can actually integrate over that interval ab and just replace everything with t. So the first term is going to be f1 subbing in this formula. This one is going to be f2 subbing in that formula. This one is going to be f3 subbing in this formula. And each of those we multiply by the derivative of that respective term, right? So it might be a bit confusing at first because it's a lot of information, but it makes perfect sense once you do an example. But the gist is just to replace everything with t stuff, right? If you can replace everything with t, then you just get a normal integral, right? You get something like 2t squared dt. That's an integral we know and love, right? So once we can do that, we'll be all good. And a nice side note is this line integral. It tells us how much work the vector field does over that curve, right? So before we had area, right? We integrate over an interval, a certain number, we get an area. But yeah, in this case, we integrate over a certain curve, and we get work. Cool. Okay, so this is when it will start to hopefully make a bit more sense. We've got a force field F, and we've got a path C. And the idea is that we're integrating this vector field over this path. And the first step, as I alluded to before, is just to replace everything with t. So instead of saying, oh, c is a straight line from this point to this point, you can actually parameterize it exactly in terms of t. And there's a very nice form of this, but when we think about it, right, we've done this kind of thing before. If you want to do a straight line from a point A to a point B, well, that's like what we did in first year, right? It's just a nice line equation, right? We start with the point A, then we do, before we said lambda, we'll do t now, we do lambda times AB. This is our position vector, and this is our direction vector. Right, so it's exactly the same process. If we want to find the parameterization from A to B, we just do A plus t times AB. But the important difference, and a very important difference from first year, is now we have a range. T lies between 0 and 1. Why is that? Because when t equals 0, we're actually at A, right? When t equals 1, we're at B. So if we want to do the line from A to B, then t has to lie between 0 and 1. Right, so remember this formula, A plus TAB, between t equals 0 and 1. You can think of it like this if you want to read over it in the slides as well, this formula too. But I prefer the second one, so I'll go through the second one. Cool. Okay, so before we actually look at this, let's just think about what we should do. Basically, we need CT. Okay, CT equals XT, YT, ZT. And as I just said, right, we're doing the straight line from one point to another. We're doing it from 431 to 635. Well, what is the line from 431 to 635? Well, that's actually the direction vector 2. So 6 minus 4, 3 minus 3, 0, 5 minus 1, 4. So we've got 204 times t. Okay, that's pretty good. So this is CT, right? And the deal is, this is all nice, but we want to kind of get it into 3 components x, oopsies, get it into 3 components x, y, and z. Right, so first of all we have, let's just write it all out. We've got 4 plus 2t, we've got 3, we've got 1 plus 4t. Those are our 3 components, right? Cool. And so now we've gotten that this is xt, this is yt, this is zt. Let's actually go back and look at this formula again, because hopefully it will make a bit more sense. Okay, so we've got CT, and we also know that now that we've gotten it into the t space, so we changed it from x, y, z to t, we can change this vague c symbol to our range for t. And hopefully we remember the range for t is going to be 0, 1. Okay, so now that we know this formula, we know that we can take each of these individually, xt, yt, zt, and we can differentiate them. So, well, xt equals 4 plus 2t, differentiate, you get 2. Yt equals 3, differentiate, you get 0. This one you differentiate, you get 4. And that's the purpose of what we've done here. Because not only do we need xt, yt, and zt, but we also need dx, dy, and dz. Right? Because then what we do is we just say, look at this column. If you know what a sum product is, it's kind of like a sum product. You just multiply this one by that one. Or not exactly a sum product, but basically you look at these 3 things and you sub them into here. Right, and so the next thing is, this is going to be f1, this is going to be f2, so that should be a 2, this is going to be f3. So what happens is we end up subbing in these three things as our x, y, and z. Because remember, our vector field, I'll just write it again, was defined as a function of x, y, and z. So I'll write it up again. It was actually equal to 2y, x, y, z, 3x, e to the x plus y. Right, those are our three things. That means that f1 is this first one. So what we do is we sub in our y into this first one. Then x, y, z is the second one. We sub in our x, y, and z into the second one. Then then this one is the third one. We sub in x and y into the third one. So yeah, that's what we've done over here. We've got, this is 2 times y is 3, so that's 2y. Then we multiply by this first one, 2 dt. The second one is going to be x, y, z, so multiply them all together. We get 4 plus 2t, 3, 1 plus 4t. But then we actually multiply by this derivative here, so by 0 dt. That turns into 0. And for the last one, we just sub in 3 to the x plus y, 3e to the sum of these two things, so 4 plus 2t plus 3, and then we multiply by 4 dt. Right, so hopefully that formula makes a bit more sense. Right, all we have to do is just sub it into those three formulae. So this is f1, f2, f3. Then we do x dt, or realistically dx, dy, and dz. And then it turns into a normal integral with t, and you end up with this thing over here. Cool. All right, now it's time to do some more exciting questions with vector fields. We have to talk about something called divergence and curl. So they're just like formulae for a certain vector field. So basically they're just operators. So for example, if we've got like x, y, z, that's our vector field. Then, well, what we just do is we just differentiate the first one with respect to x, that's 1. Add it to the second one with respect to y, that's also 1. And then add it to the last one with respect, this should be a 3. With respect to z, we get a 1. That's a 3. Cool. Yeah, then we look at curl as well. Curl is a bit more tricky, and because it's such a tricky formula, there's like a mnemonic you can use, which is the determinant definition. So if you remember our determinant, you can go across a row, and with each term, I, you multiply it by the determinant over here. So you say I times the determinant excluding this row and this column is over here. You do the same thing with j. Then you multiply that by, you exclude this column, this row, d on dx times f1, d on dz times f3. And then you do the last thing with k, and you do d on dx, d on dy, f1, f2. And that's our formula for curl. We'll do an example later, but basically this is just a nice way to remember it. Cool. Yeah, so why do we actually care about curl? Because if curl is equal to 0, then it actually makes our line integrals a lot easier. It means, number one, this is the first property, that we can say that g, if g is 0 curl, it means that g is actually a gradient of a function. So remember from before, like when we saw gradients, it's going to be equal to df dx, df dy, df dz. So what this is saying is kind of, if g has 0 curl, then you can find it as a derivative of another function, right? We can actually say that this is actually equal to a gradient, right? And then g is also called a conservative field. And if that's the case, then we have this really awesome property. So using this function phi, if we've got a curve and it starts at the point A, ends at the point B, I don't know what it does in between, but we start at A, ends at B. If this is a conservative field, we can just take that function. This is like the antiderivative, right? Because we're saying that f is equal to the gradient of phi, which means that this is kind of like the derivative. This is like the antiderivative, right? Then we can do the exact same thing as we would in a 1D function, when we do phi of b minus phi of a. Right, so that's pretty good. Phi of b minus phi of a. right? So it doesn't matter what it does in between. It could go anywhere. But all we need to know to calculate this integral is where did it start and where did it end up. And that's kind of like exactly the concept of an antiderivative. Cool. So let's do this example. The first part is just doing a formula. So finding the curl of f. Right, we've got this scalar field and find the curl of f. So what is f? Well, f is actually defined as being equal to not this. That's not f. It's equal to the gradient of phi. So if we think about that right, that actually means that by definition, this is conservative. And conservative fields are also irrotational. Right? So if you have the gradient of any function, it will always have curl 0. Right? Because conservative and irrotational, meaning 0 curl, they're actually the same thing. So already, we don't need to do any calculations. We know it's a gradient, so we get the curl for free. And the curl equals 0. Now we're on our way to calculating the integral. And it wants us to calculate a line integral along the straight line path from 1, 0, 1 to 5 pi 1. And I'd love to parameterize another straight line path, but in this case we actually don't need to, because we're given this really awesome property that it's conservative. And if this thing is conservative, then what that means is we don't need to do any parameterization. We just do this thing from before, right? Phi of b minus phi of a. In this case, we're actually given that f is the gradient of this function. So already we can use this function as our phi. Right, so all we need to do is just calculate this function at our endpoint, so 5 pi 1, and then calculate it at our starting point, 1, 0, 1, and take the difference. So we'll do exactly that. Right, so it's just a matter of subbing in when we get to. Right, this is another question that's kind of cool. It's about line integrals, and we first need to show that it's a conservative vector field. So unfortunately, in this case, we're not given that it's a gradient of some function. If we were given that, we could just say curl f equals 0. In this case, it looks like we might have to do the calculation. That's okay. We love the calculation, right? So remember, curl f, if you can just try to remember this formula as well, curl f equals I, j, k, and then you put the 3 derivatives. So partial derivative x, partial derivative y, partial derivative z. Then this one is the 3 components. Right, and so now that we've done that, it can be a bit tedious, but we will do it together so we won't get too sad. Okay, so curl f equals this determinant. Okay, and so how do we evaluate this determinant? I touched on this really briefly, but basically you just go across the row. Start at I, and then I corresponds to the matrix with these columns removed. So you just say go across, go down, remove those columns, and then you multiply I by this determinant. So I times that one. Yeah, then we go to the next one. We've done I, and now we actually start alternating signs. We do minus j, and then we do that or times, and we do the same process. So cut out this row, cut out this column, and we're left with these 4 things. Just do that. And we're all good, right? So we've got that determinant. And you can guess what the final term will be plus k times the determinant of everything excluding that last column and that first row. Right, so we're all good. We get d on dx, d on dy, yz squared, and then xz squared. Cool. That's looking pretty good. And then once we've done that, all we need to do is just calculate 2 by 2 determinants, which hopefully we're okay with, because it's just going to be a matter of doing this times that, minus this times that. So just do the difference of the 2 diagonals. Right, so you end up with something like d on dy, 2xyz plus 3, minus d on dz, xz squared. And you keep on going down, you'll get the same kind of stuff, and we'll get this over here. Cool. So yeah, you can see the exact process we've used is the same, just do these three determinants, do this differentiation, and then just evaluate the differentiation. So for example, this is the partial derivative of this formula with respect to y. That means you get 2xz. This is the partial derivative with respect to z. So you get x times 2z, which incidentally is the same, so we get 0. And you can kind of see where we're going with this, because all of these are equal to 0. If you do the same thing on each one, you'll get 0 regardless. And so you get 0i plus 0j plus 0k equals 0. So hence, F is a conservative vector field, right? Because conservative which means that we're equal to a gradient of some function. Is the same thing as being irrotational. So curl F equals 0. Right? And yeah, we're basically done. Okay, now this gets to the more intense part of the question. We've got a path, and apparently it starts at 3, 4, 7, and it travels anti-clockwise 4 complete revolutions about this circle, x squared plus y squared equals 25 within this plane, where it turns to the point, then it moves diagonally in a straight line to 4, 1, 0. So it seems like this point's a bit out of control, but when we think about it, right, who even cares, right, what happens? Right, with conservative fields, this integral just turns into the difference between the endpoint and the first point. All you have to do is just calculate this function. Right? So it doesn't matter if it went anti-clockwise, doesn't matter if it went diagonally, right? It doesn't matter if it went to like the point 1,000, 1,000, 1,000, and back. All we care about is where it started and where it ends off. So it's trying to distract you, but the point is just we need to find this thing over here. And how do we? Yeah, exactly. So when we have a conservative vector field, we don't need to go to the trouble of parameterizing it, right? Just really the emphasis is just finding this phi. Cool. And here as well, think about what the start and the end point is. It starts over here, 3, 4, 7, and it ends at 4, 1, 0. Cool. Okay, but it's not actually super simple to calculate phi. Because remember, phi is defined as gradient of phi equals f. And when we think about that, that means that, well, let's just say gradient of phi, that's equal to d phi dx, d phi dy, d phi dz. It's almost like we're solving 3 equations. This one has to be equal to d phi dx. This one has to be equal to d phi dy. This one has to be equal to d phi dz. And in these equations, these examples, we always just want to do something very simple, which is just try to solve this system of equations. And it's not actually as hard as it looks. All we have to do is just start off with one of these equations. So let's think about this for a second. If the derivative of phi with respect to x is equal to yz squared, then can't we just integrate with respect to x? We'll get phi xyz is equal to, well, this is basically a constant with respect to x. So it'll be x times yz squared. And then we have a constant in a sense. But when we think about it, right, this constant just has to be a constant with respect to x. Because let's say, for example, if we had something like yz, then if we were to differentiate this with respect to x, this would just disappear, right? Right, so realistically, it's not a constant anymore. It's going to be a function of y and z. So that's a really important point. When we integrate with respect to x, the leftover constant, so this is a leftover constant, needs to be a function of the other 2 variables, so c of yz. So that's our first step. Yeah, and we've got this over here. We're off to a nice start, because in a way we have kind of isolated the x component. Right, we've calculated phi is equal to xyz squared plus this c component here. And all we know is that this has to contain x, and this can't contain x. So if we keep on doing this, we might actually reduce it down to a function we actually know. So yeah, we are close, but now we need to try to solve for c, y, z. We've squeezed everything we can out of this first equation, so let's turn to these next two equations. So first of all, let's try this equation here. So we're given that phi is equal to x, y, z squared plus c, y, z. So maybe we can just differentiate with respect to y. Right, let's do that. We get d phi dy equals this thing is yz squared plus plus the partial derivative of c over there. Okay. So what does this mean, right? We've got sorry, my bad, that should be xz squared. We know that the derivative is equal to this, and it's also equal to this. So we can compare these two, and that means that we know that the derivative of c with respect to y is equal to y, right? So in a way, right, let's just equate that. We can actually integrate with respect to y. That's about what we did before, right? And then what we get at the end is we just get another constant. But this time, remember, we can't just do constants anymore. It has to be a function of what's left over. So we're integrating with respect to y. So what's left over is z. Cool. So yeah, that's what we'll do over here. We've equated these two things. We've differentiated, we've equated. And now we found out that that's equal to y. And then we integrate, but we acknowledge the fact that this constant, so to speak, can be a function of the remaining variable. Cool. All right, so yeah, basically now we take this back into our original equation, and you can see the idea is we went from having phi equals xyz squared plus c, a function of y and z, and now we've kind of isolated the y component. The y component is over here, and now we just have the z component left over. So if all goes to plan, we do the final step, we'll be left over with nothing, right? We'll isolate the z component too. And yeah, you guessed it, final equation time. Cool. All right, so let's take this and differentiate again. With respect to z this time, we'll get 2x, 2xyz plus, it'll be nothing because that disappears. And then this turns into c1, and it'll be the derivative with respect to z, z. Cool. So again, we found out more about this part. The derivative of c with respect to z is equal to 3. So that's actually something we've seen before. So c1z needs to be equal to 3z. And this time we do have a constant, but it's finally a constant that's free of any other variables, because, well, there are no variables left, right? So we're basically done, right? Let's see all this, we equate again. And then finally, cz equals 3z plus c, and so we've identified this function. Cool. So now we've got this. And you can kind of guess, because we've got this thing where it's like phi b minus phi a, it's good that we have the constant, because that will actually cancel out. It doesn't matter that we don't know what the constant is. So all we have to do now is just calculate, just sub in this thing, calculate it, sub it into the ending points, so b, the starting point, so a, and we'll be all good. Cool. And this is just more algebra, arithmetic, and we're all happy. Okay, so now we're moving on to something else that's equally exciting, which is double integrals. So double integrals, it's kind of like you're calculating an integral over a region instead, right? So before we calculated integrals over line segments, now we're actually calculating integrals over regions themselves, right? So, and when doing a double integral over a nonlinear domain, we generally want to sketch the domain to see what we're sketching. So in this example, it's good to draw 6 minus x squared, good to draw y equals x, and the y-axis. And we get something that looks like this, right? So this is 6 minus x squared. And you can kind of see if you draw out y equals x, it will intersect somewhere. And you can try to find the intersection point. In fact, that's really important. Let's draw it out. Y equals 6 minus x squared, y equals x. So that means that 6 minus x squared equals x. I'm just solving that. I won't go into it, but you know the answer has to be 2 here. Okay. This is the region over which we're integrating. And the idea with double integrals is if you want to integrate over a domain, it's kind of like you're integrating an integral. So think about the original case with double integrals, which we didn't go through, but which you would have learned in lectures. So you've got like a rectangle, and you're integrating a function over this rectangle. What you're basically doing is you're taking the integral, let's just say we're doing the square, this square. You're integrating this integral first of all, and then, well, and then what you do is you integrate the integral from 0 to 2 itself from 0 to 2. It's like this integral is, you're taking cross sections across this graph, and it keeps on going along. And that's why we have 0, 2, 0, 2. So we want to think about the same kind of principle over here when we're doing these regions. What we're doing is we're integrating an integral. So for example, this first one is going to be the integral from 0 to 6. As we go across in this direction, we do the integral from this point to this point. Then we do the integral from this point to this point. So yeah, that's kind of the point of a double integral. We're integrating an integral. Right, so what we want to think about is, what do we want on the outside? When we have a dx dy, and in a double integral we have dx dy, then the dy thing is what you're integrating with respect to y. It means you're going up. Right, so this integral is with respect to x, so it's a horizontal one. So we've got something like this. I might rub this out just to make it a bit clearer. This is the integral from with respect to x, and you're basically integrating that integral with respect to y. So hopefully we can see how this thing, having the dy on the outside, corresponds to this kind of thought process. We're integrating this line segment as it goes up and down. And if we do it the other way around, dy dx, first of all, this is an integral with respect to y, so a vertical integral. So it's kind of the opposite. We're doing an integral along the vertical axis, and we integrate that along here. So hopefully we can all see why this second case corresponds to number 2. Right, so that brings us now to our 2 options. So how can we kind of define this integral? So which option works better? Right, which will we rather do? Would you rather integrate this line as it goes up and down? Or would you rather integrate this line as it goes across and across? Well, when you think about it, one of them is smoother than the other. So if we do this one, it goes up, then it suddenly starts going down. But if you do the other one, it's pretty steady. These both keep on changing in the same direction. Right? So we're tempted to do the one where we integrate with respect to y first, then we integrate that one with respect to x. Okay, so hopefully that all makes sense how we're thinking about this. We're going to prefer to do the one with dy dx. But the next question is, how do we actually determine this? So remember, this is kind of like an integral of an integral. So first of all, what is the integral that we're doing inside? Well, that's the integral from this point at the bottom to this point. And it's kind of like we're integrating a function of x, right? Because this integral is a function of x. It's the function, it's an integral at this point x. Right, so everything inside here needs to be determined in terms of x. Right, so yeah, you can also think about it as, if we've got a dx here, everything over here needs to be in terms of x. Well, the function is pretty simple. We've got xy squared, and that will never change. And then what we do is we see, what is this lower bound here? Well, x equals y, right? We're looking for the height. So that means that this height has to be equal to x. So we go from x. And the other thing is, well, this is equal to 6 minus x squared. So we go from x all the way up to 6 minus x squared. Okay, so that's the integral that we're integrating, if that makes sense, right? And then what we do is we say, let's integrate that integral from this bottom point over here to this end point down here. And we talked about this as being the point 2, 2. So that's from 0 to 2. Cool. So hopefully that makes sense. That's kind of how we break down these double integrals. We want to think about it as we're integrating an integral over a line segment. Okay? And try to do the one that's more smooth. If you want, you can think about this one in your own time, but because we're short on time, we'll just look at this one. Cool. So having looked at that double integral, yeah, we'll use the first one because it's simpler, and we generally can identify which one will be simpler just by saying, oh, this is the integral such that the inner bounds vary smoothly. So we said this one is smoother than the other. Yeah, so now we've kind of broken it down, exactly what we just said. And what you want to do is just do the one on the inside first. Right, so this thing over here, how did we get this? Well, this is an integral with respect to y, so just treat x as if it's a constant. Right, we get a third times x, and then we do y cubed. Right, and also the bounds. So the bounds are x and 6 minus x squared, that's correct. But oftentimes you might get a bit confused when you see 6x squared, x, y, x, all of these crazy variables. So it's often better to say, well, what variable is equal to 6 minus x squared at the top? Well, that would be y. And then we do y equals x down there. Cool. And basically you just sub that in, and it turns into a nice integral. Cool. Any questions, just shoot in the chat, but hopefully that all makes sense. Cool, and there's one more thing we want to do with double integrals. We want to look into integrating over a different coordinate system. So we've integrated with x's and y's, but it turns out we can integrate with r's and dr's and d thetas. Well, before we think about that, let's just think, well, this thing, so let's just write it out again. We, for example, had, I'll just take this as an example, 0 to 2, x and 6 minus x squared. What do these bounds mean? They tell us where y varies. So y can go between x and 6 minus x squared, and x can go between 0 and 2. Well, there's no reason why we can't do this with polar coordinates, right? Because let's say, for example, we want to integrate over a circle. Well, we can also define that in terms of r and theta, right? Well, theta goes between 0 and 2 pi. And r, well, that can be just between 0 and this radius here. Let's say it's radius 3. R goes between 0 and 3. Right, so there's no reason why we can't do the same thing with polar coordinates. So if we can express that same region, let's just say we have a given region, omega. If we can express that same region in terms of polar coordinates, which means that having x and y in this region is equivalent to having r and theta in this other region, then we can actually do the integral with polar over there. Let's just imagine our bounds. Somehow, we're going to have r goes between 0 and r, and also we're going to have theta goes between 0 and pi on 2. And then at the end, we'll have r d theta, d theta. Sorry, r d theta. And just be mindful that the one inside has to correspond to these limits here. So r has to go between 0 and r, that's correct. D theta has to go between 0 and pi on 2. We wouldn't be able to switch these around, for example. That wouldn't be allowed, because then we somehow have r lying between 0 and pi on 2, and we somehow have theta lying between 0 and r. Cool. Okay, so yeah, back to what we're doing here. So we've got e equals minus x squared plus y squared, r d theta. Okay, so well, now we have to express x and y in terms of r. So usually what we can do is we can say x is equal to r cos theta, and y is equal to r sine theta. But in this case, it's a bit simpler, because we know x squared plus y squared, well, that's just going to be the radius squared. So we've got e to the minus r squared times r. Cool. All right, and so what that means, right, is we've got basically a nice integral. There's no more work to do because we've got this polar integral. Yeah, and that's what we've got down here. Just integrate over here. So again, just do this inside integral first, and that ends up being something as simple as that. And then we do the integral with theta, which turns out to be 4 pi on 4. Awesome. So that's our first part. Now to the second part. Somehow they want us to leverage this into what we just calculated, into calculating e to the minus x squared from 0 to infinity. Well, there's a big difference, right? Because this is on the first quadrant from the quadrant of the circle in the first quadrant. So that's going to be over here. Then somehow this is over infinity. So generally the first step will be take the limit as r goes to infinity. Because otherwise we have no hope of getting this. Okay. So what we'll do here is we'll say take the limit as it goes to infinity. This side goes to, well, r goes to infinity, it turns into pi on 4. But what about this side? Let's think about this. What happens to the region as r goes to infinity? This is our region, the quadrant of the circle. As r gets really big, well, it just becomes the entire first quadrant, right? So this turns into 0 to infinity, 0 to infinity, because that represents the first quadrant. All right, we're in good shape now because it's looking a bit better. We've got e to the minus x squared and y squared. Cool. And what we notice is whenever we have a double integral and we have something like this, we can try to separate it out, e to the minus x squared, e to the minus y squared. And because this is a constant with respect to x, we can just take it out there, right? So what does that look like? It looks like this, right? 0 to infinity, e to the minus y squared times 0 to infinity, e to the minus x squared. And this becomes totally separable, right? Because this is x and this is y. And that's what we've done over here. Oh, the screen froze apparently. That's not good. Can you hear me? Maybe I'll just try again. Something's going wrong. Oh, awesome. Thank you so much. There is a bit of a delay. I'm not sure if you've noticed between you guys saying stuff and me seeing the chat. Give me a moment while I reposition the scene. And it should be all good now. I'll just double check. Okay, it's fine now. I will continue now. Yeah. So I was stuck on. Oh, that's really tragic. That's a long way back. Maybe I'll just check what we last did. Okay. Yeah, what I might do is while I'll just see if I get a response, but it should be fine now. I can see it working on my screen too. Yeah, it's working on my screen. What I'll do is I'll just briefly go over what I did because I think it might have been missed. But basically, we're just trying to evaluate this integral, and we just convert this region into polar coordinates. So x squared plus y squared minus r squared lies in the first quadrant. It's this thing. So that means that r lies between 0 and r, and also theta lies between pi on 2 and 0. Okay, so just convert that over here. And you'll notice over here we also get r d theta. So I'm just going to speed run this question, as you can tell. But basically just do that and we're all good to go. And you get this answer. And the second question was somehow we need to change this and calculate the integral from 0 to infinity of e to the minus x squared dx. That's the second part. It says hence, find this part. And what I was saying, presumably without any visual aids, which made it a bit difficult, but what you can see is that basically we've got something with a finite integral here and something with an infinite integral here. So to try to do this, we need to take the limit as r goes to infinity. Right, we'll take the limit as r goes to infinity, right? So what we do is we try to take this limit. So we get, on this side, it just turns into pi on 4. But on this side, this left-hand side, this is remember this side is the quadrant of the circle x squared plus y squared equals r squared. So as r goes to infinity, this just like expands and it fills up the entire first quadrant. So we end up getting this. That's where we were just then. This equals pi on 4. Right, because we took this side and we took this side as r goes to infinity. And then the last thing we did, I'm assuming the screen is fine, right? Yeah, the screen is fine. The last thing we did then is we said we want to try to split this up into two integrals. So because we have e to the minus x squared times e to the minus y squared, it's sort of separable, right? When we have a product of two functions, it's separable. And what we can do is we can just take these apart. Right, and it turns out these are the same. So if we've got this times this equals pi on 4, well, that just means that this integral squared equals pi on 4. So then this is equal to root pi divided by 2. Cool. So hopefully that wasn't too disruptive, like the screen randomly disappearing. But yeah, hopefully you can see how that question works now. Any questions, just let me know when you can. Cool. So we're going to finish off with one very cool thing about matrices. And basically we're going to cover diagonalization. We're going to do some quadrics, and we might get time for some differential equations. Okay, so first of all, a pretty simple question to ease into it. We've got a matrix. We want to show that this thing is an eigenvector of the matrix. So over here, the definition, which we know from first year, a vector v such that if we take a and multiply it by the vector, we get a multiple of the original vector. So all we have to do is just say, hey, if we want to see this as an eigenvector, just take a, multiply it by this, and then see what we get. In this case, we actually end up getting minus 4 minus 2 minus 2, which actually ends up being minus 2 times 2, 1, 1. And so our vector is an eigenvector of eigenvalue 2. Cool. Yeah, for the second part of the question, we're using something called diagonalization. The question actually is, this next part, diagonalize the matrix A. So to do that, we actually have to find all of the eigenvectors. And that's quite problematic because number one, you know, we might use the process called finding the characteristic polynomial, but in many cases we can actually use some information that we personally have, right? And in this case, we actually know that the eigenvalues are minus 2 and 1, right? But the problem is, in this case, we're not actually given all of the eigenvalues. So something you might remember from first year too is a 3 by 3 matrix has 3 eigenvalues. And an n by n matrix has n eigenvalues. So the fact that they've given us -2 and 1 is great, but we actually need one more. But whenever we are trying to find a last remaining eigenvalue, there's actually a shortcut we can use called the trace. So the trace of A, which is equal to the sum of these diagonal entries, is equal to the sum of the eigenvalues. We've got -1 plus 2 plus this last one. Right? So what's the trace in this case? It's -5 plus 4 plus 1 equals 0. So 0 equals -1 plus lambda 3. And hence lambda 3 equals 1. Cool. That's our remaining eigenvalue. So we know we have eigenvalues -2, 1, and 1. So that's pretty good. It means that if we want to find all the eigenvalue vectors, we can just take these eigenvalues. And that's what we've done here. The trace of a matrix is equal to the sum of the eigenvalues. Cool. So the deal is they've already given us the eigenvector with eigenvalue -2 because we already found it. We got that this is equal to -2 times 2, 1, 1. So now what we have to do is find the eigenvectors with eigenvalue 1. And I won't go too much into this because it's from first year, but if AV equals V, that's the definition of an eigenvector of eigenvalue 1, and that means that A minus I times V equals 0. And so what this reduces to is just finding the kernel of A minus I. Right? So finding the vectors such that A minus I times that vector is equal to 0. Right? So then we just do A minus I, we get this. And you can see why we've got so many vectors that are in the kernel, because all of this disappears, and we end up getting -1, 1, 0. And at this point, we need to try to find these eigenvectors. So what we do is we say, well, what vectors, when you multiply it by this, give you 0? Like, you could use our first year technique of doing non-leading columns, doing parameters, but in these cases, if you can find these two vectors instantly, it's a lot easier. So for example, -1, 1, 0, that means that 0, 0, 1 is in the kernel. Right, because 0, 0, 1 times -1, 1, 0, well, that's just going to all overlap. We'll get -1 times 0, 1 times 0, 0 times 1. This will be equal to 0. Right, so that's in the kernel, first of all. Let me know if you have any questions, because this is kind of building on what we did in first year. But that means that one of our eigenvectors, is equal to 0, 0, 1. Right, and the next thing we do is we say, let's try to find another one. So what if the first entry of our vector is 1? Then we kind of need to be able to cancel it out, right? Because this times this vector needs to be equal to 0. So first of all, we've already got, because this is how matrix multiplication works, 1 times -1. Then we'll get this next one times 1. Right, so that's equal to -1. That means that this one times that one needs to cancel it out. So I'll write that out a bit more carefully because it's a bit confusing. We've got -1 times 1 plus 1 times this mysterious thing that we're trying to find out plus 0 times something else equals 0. Which means that the last value we're looking for is actually just equal to 1. So 1, 1, 0 is another eigenvector. Right, hopefully that makes sense. That's how we try to find these eigenvectors. So now that we've gotten that, yeah, we've got v1 equals this, v2 equals this. Okay, so now we want to talk about diagonalization, and diagonalization is all about diagonal vectors, matrices. Right, and a diagonal matrix is one where you have zeros basically everywhere. Basically everywhere, except for these diagonals. Right, so that's a diagonal matrix, and the deal is that if we have a diagonalizable matrix A, then what we can do is we can actually write it in this form. This will be a diagonal matrix, and this will be some invertible matrix. And it looks really complicated, but the process is super simple. All we do is we say D is an n by n matrix where the eigenvalues are along the diagonal. So in this example, we found the eigenvalues already. It's -2, 1, 1. So already, D is going to be equal to minus 2, 1, 1. And it turns out Q is just as simple, right? We take a matrix and we arrange the eigenvectors in an order corresponding to these eigenvalues. So the eigenvector of eigenvalue minus 2, we put in this first column. So we put in the first column and we get, what will it be? It was the matrix we saw at the very beginning. So minus, where is it? 2, 1, 1. 2, 1, 1. Then this next one is the eigenvector of eigenvalue 1. Replace that just with the eigenvector. So we get 0, 0, 1 was one we found. And the other one we found was 1, 1, 0. Right? So the order doesn't really matter. In this case, we've done it in a slightly different order. But we need to make sure that the order for D corresponds to it. So this has to be minus 2. This is 1. And this is 1. And then it's really simple to say we've got A equals Q, D, Q inverse. Cool. All right, and so that's all we need to do. We've diagonalized the matrix. Okay, time for the most hefty part of this seminar, which is about conics and quadrics. So hopefully we've seen shapes like maybe x squared plus y squared equals 5. That's a circle. And if you've seen a variety of other shapes, you would have also seen x squared plus y squared plus 3z squared equals 5. But basically, these are all very simple shapes that you can all define, right? So this is, for example, an ellipsoid. And if you check your lecture notes, you'll find a list of shapes that look like this. And they tell you basically how do you identify what shape it is. So I could give you x squared plus y squared minus 7z squared. And you can check your lecture notes. It will tell you if you've got 2 positives, 1 negative, it's this shape. Right? And if it's 1 positive, 2 negatives, it would be this shape. The idea is that shapes like this with only x squareds, y squareds, and z squareds, they're actually pretty simple to classify. And they're all called conics and quadrics. The conics are the ones with just x's and y's. And the quadrics are the ones with x's, y's, and z's. Unfortunately, life is complicated in general, and so is maths. And so sometimes we have terms like xy and yz and xz. And things get a bit harder, but it turns out that we can use eigenvectors to save our life. If we have a shape like this, we can actually somehow show that a shape like this is a rotation of another conic with just these terms. Right? Something without any xy, xz, and yz terms. Right? And so to identify, there's a very simple process that we use. Okay, so I say simple, but there are lots of steps, so let's just get an overview. So first of all, try to express this curve in the form xt, ax. And what is x? X is the point, so in this case it'll be x, y, z. Then we do some matrix A. And then we do some vector x. Okay, so yeah, we've looked at this quadric and we've said we don't like these terms, so we're going to try to break it down. And in this case, we've tried to express our curve in this form, xt, a, x equals c. We'll explain why in a second, but then once we've gotten that a, we can do the eigenanalysis, find the eigenvalues and the eigenvectors, and then finally, we diagonalize a into a special form. So we just did diagonalization, but this diagonalization is a bit different because there's a condition that we need for Q. Q needs to be orthogonal. And we'll talk about that later, but right now let's just try to understand this main process. Break it down into xt, ax equals c. Break down a into its eigenvalues and its eigenvectors, then diagonalize such that this Q is orthogonal. And then we'll be all good to go. Cool. Step number 1, try to break this down into xt, ax. And it turns out that there's a very simple process you can use. So we want to change this to some formula with x, y, z times a matrix times x, y, z. Okay, how do we do this? Well, some of the terms are very simple. So if we think about this term in the process of multiplication is going to be multiplied by x, and it's going to be multiplied by this x too, right? If you're trying to visualize the matrix multiplication, you'll get x times that plus y times that plus z times that. So this ends up being something times x squared. So the first tip is that all of these diagonal terms correspond to these coefficients. So this one is 5. This one, which is y, is actually equal to 3. And this one, which is z, is actually equal to 4. So hopefully that makes sense. The diagonal elements correspond to these terms that we love. Right, so these quadratic terms, they turn into these things. Cool. All right, the next part is we've got these mixed terms. And the way we think about this is mixed terms correspond to x corresponds to 1, it's the first component. Z corresponds to 3, it's the third component. So there are actually two terms it corresponds to. The 1, 3 element of the matrix, which is over here, and the 3, 1 element of the matrix, which is over here. And it turns out that if you write any two numbers that add up to 2, then it'll work. Sorry, any two numbers that add up to 4, it'll work. Right, so split up 4 into 2 and 2, and we'll get something that works fine. Okay, so but what we want to do is, because we want this matrix to be symmetric, we usually split it up in the middle. So divide this 4 by 2, and you'll end up with 2 there, 2 there. What about these terms? This is the 2, 1 term of the matrix. This is the 1, 2 term of the matrix, right? So what that means is that we've got 1 and 2 is x and y. So this term over here will correspond to the coefficient of x, y. I'll just try to tidy this up a bit. But yeah, this corresponds to the coefficient of x, y. But because there's no x, y over here, this will just be 0. Last of all, we've got yz. Yz is the 2, 3 term, because y is the second one, z is the third one. And so this 3, 2 term, this is the 2, 3 term, they will both be equal to something such that they add up to 4. So you split it up into 2, and you get 2, 2. Right, so hopefully that makes sense. Just to recap, these terms over here, they're the diagonal terms. Then these mixed terms, you have to find the corresponding one in the matrix, and you split it in 2 parts. So that's 2 plus 2, and then this thing is 2 plus 2 as well. Cool. So hopefully that makes sense. That's how we find the matrix A. And that's what we've got here. Alrighty, so the next step is to calculate the eigenvalues and eigenvectors, and that's really important. We'll see why in a second, but I'll just show you the actual answers, because it's a first year problem. We're not going to spend too much time actually doing this calculation. Right, for now we can take for granted that we've got these eigenvectors and eigenvalues. Cool. And now we can diagonalize, because we know the process is really simple, right? We just do this, right? M, D, M inverse, where this has the eigenvectors, and this has the eigenvalues. Right, so it's pretty simple. All we have to do is just express our curve in the form. We have to diagonalize. Right. The problem is that there is this condition of orthogonality. Right, so we can't do any old matrix. We need to somehow change our matrix. And an orthogonal matrix is a matrix such that the columns are actually orthonormal. And that means two things. Number one, they have to have magnitude 1, and they also have to be mutually orthogonal. Right, so they all have to be perpendicular. And looking at this, right, which is our first thought, we just put down the eigenvectors here. Right, because we know this has eigenvalue 1. This has eigenvalue 2. This is eigenvalue 3. Sorry, that's 4. This is 7. Okay, so the idea is basically that we've got Just checking that this is working. Yeah, it's working. Yeah, the idea is that this is a perfectly fine method of diagonalization, but the only problem is that Q is not orthogonal, right? There is good news though. With a symmetric matrix, that's why we did a symmetric matrix. It's always going to be possible to find orthogonality. So already you can see that these vectors are actually perpendicular. Take the dot product, minus 1 times minus 2, minus 2 times 2, plus 2 times 1, which equals 0. So these are orthogonal. You do that for all pairs of them, they'll be orthogonal. So that's really good news. That means the only thing we need to change is that the magnitude needs to be equal to 1, right? So yeah, it's pretty simple. We just scale it by the magnitude. This has magnitude 1 squared plus 2 squared plus 2 squared square root, which equals 3. So realistically, you can just divide by 3. And now this is a unit vector. Same thing over here, this is a unit vector too, as is this. Right, so hopefully that all makes sense, right? Because we are just basically taking this and turning it into an orthogonal matrix. And then we are ready for our beautiful diagonalization. And what we'd expect to see with any diagonalization is we've got M, D, M inverse, right? So we might say, why is there a transpose there? Well, the reason is because the transpose of an orthogonal matrix is the same thing as its inverse. So now our formula is actually going to be A equals Q times D times Q transpose. All right, and this is where our question all comes together. We're in the home stretch now. So remember we had from before, xt times A times x equals 1. And that's all well and good, but we talked about how we want to break this down into a diagonalized version, right? So let's take xt, qd qt times x equals 1. Okay, so that's broken down now. And that's where we've got this. And why do we think we want this? Because if we have a diagonal matrix over here, and we do something like this, right? Let's just say we've got 1, 1, 1 times x, y, z, x, y, z. This will actually correspond to just, remember how we were forming our matrix before? This corresponds to the x squared term. This corresponds to the y squared term. This corresponds to the z squared term. So if we have a diagonal matrix, it's kind of like those perfect conics that we actually understand, those perfect quadrics, right? Because we said this before, I will just scroll up really quickly. These quadrics with just x squared, y squared, and z squared terms, we know what they are. There's this nice table in your lecture notes that tells you basically what are these types of shapes, right? So that's why we want this diagonal matrix. And because we want that, what we do is we say, let's actually change this over here. Everything outside of the diagonal matrix, let's change, right? So we've got qtx here. And if you actually think about this thing over here, this is actually equal to qtx transpose, right? Because let's just write it out. If you take the transpose, you take the transpose of both terms, and you switch the order. So yeah, xtq is equal to qtxt. Right, so remember this transformation, it's really important. Because what that means now is if we actually replace qtx with some other variable, capital X, right, then we've got exactly what we want. We've got xt, let's just say x equals x by z. We've got xt times d equals x. My mistake, sorry. Xt times d times x equals 1. And that's exactly that kind of conic we wanted, right? With just x squared, y squared, and z squared terms. Right, so hopefully that all makes sense, right? Because we've now got this beautiful little formula with just d's, with just a diagonal matrix. But all we had to do is just replace qtx with x. Okay, so yeah, that's what we'll always want to do. We basically just replace qtx with big capital X is equal to x by z. And now we've got a beautiful formula here. Okay, so let's just check what we had before. our diagonal matrix was equal to 1, 4, 7. And we know this is equal to 1. So if we remember like what we were doing before when we were forming our matrix, these represent, as I said before, x squared, y squared, and z squared. So realistically, now that we've got our diagonal matrix, it's beautiful, right? We've got x squared plus 4y squared plus 7z squared equals 1. And that's a shape we actually know about, right? If you check your lecture notes, it says explicitly this must be an ellipsoid. Right? So basically all of this magic was just meant for us to basically reduce it to something like this. X times d times x equals 1. Cool. And this is an ellipsoid. It looks like this. So your lecture notes will have an authoritative guide on how to identify the basic quadrics. Like, that's not our focus here. Basically, our focus here is on trying to break it down to those basic quadrics. Okay, and this is the final part that might be a bit intimidating at first, but it's actually quite not too tricky. So the idea is that Q represents a rotation. Every orthogonal matrix represents a rotation. That's something cool about orthogonal matrices, right? So, or they could be a reflection as well, but generally we can just think of them as rotations. Okay, so the way we can think about this is that Qt equals x, right? My mistake. Qt times x equals x. And also, x, x, lowercase x, the real x, equals q times x. Okay, so just try to wrap your head around that. Q times big X equals x. So what that means is if you want to get from x, the x space, to the little x space, you want to multiply by q. So for example, let's just say we've got in the x space, we've got an ellipsoid, right? This is kind of an ellipsoid, but yeah, this is an ellipsoid, right? I'll just draw the third axis too. Yeah. In the big X space, so big X space, we've got a perfect ellipsoid. And we know the structure of an ellipsoid, right? We have an axis over here. That's our, let's just say this is the x-axis, that's the y-axis, that's the z-axis. This is going to be 0, 1, 0. This is going to be 1, 0, 0. And this is going to be 0, 0, 1. Right? So we've got these three axes. This is the big X space. And we want to get from the big X space to find out the little x space. Right? To get from the big X space to the little x space, we need to multiply by q. Right? So that's the whole point, right? If x is equal to q times x, then to get from this space over here with the ellipsoids, we need to multiply q by x. So, for example, the principal axes of an ellipsoid, they are 1, 0, 0, they are 0, 1, 0, and they are 0, 0, 1. Right? Because an ellipsoid, if you look at it, it actually looks like this. And these principal axes are these things over here, the x, the y, and the z. Right, so now that we've gotten that, right, essentially now that we've gotten these three axes, if we want to go to the little x space, we just multiply by q. So it means that the three axes of our actual ellipsoid in the little x space are q1, 0, 0, q0, 1, 0, and q0, 0, 1. So looking at this now, we want to find the principal axes, the type of surface, and the points, if any, on the curve, which are farthest from and closest to the origin. Right, so we'll just look at the principal axes first. That, as I said before, q1, 0, 0, which is equal to, I'm just writing out q. Q is equal to, from before, this thing. So q times 1, 0, 0 is just the first column of this. And q times 0, 1, 0, q times 0, 1, 0 is just equal to the second column, and q times 0, 0, 1 is equal to the last column. Okay, so that's why we get the three principal axes are those three columns of q. The next question is basically asking us the point closest to the origin on the xyz plane. And to do that, we have to think about an ellipsoid. So we've got x squared plus 4y squared plus 7z squared. The idea is that to get the ellipsoid, we want to find the intercepts of each one. An ellipsoid is kind of defined by its intercepts, right? So the x-intercept is going to be equal to when y and z are equal to 0. What that implies is that we have x squared equals 1. So we've got 1, 0, 0, and minus 1, 0, 0. The y-intercept is x equals z equals 0, and we end up getting y squared equals 1 and 4. So we've got 0, 1/2, 0, and 0 minus 1/2, 0. And the last one is our z-intercept. That's x equals y equals 0. Then we get z squared equals a 7th. So that means we get z equals 1 on root 7. And what that means is we've got our last one, which is equal to 0, 0, 1 on 7, 0, 0, minus 1 on 7. The point is that if you actually go through the process of finding the coordinates, this isn't our focus for today, but you'll find that one of them is very close to the other. Right? These are the closest points to the origin. So the focus is now the point closest to the origin on this x space, this big x space, is equal to this. So to get to that corresponding point on the xyz plane, which is the original quadric, we just multiply that. We multiply q by that. And that ends up giving us this point here. Cool. So yeah, just with quadrics, we want to think about this process. First of all, let's go back to the process. Find this a thing. Find the a such that the curve is in the form xta, x. Right, then find the eigenvalues and eigenvectors of a. Then diagonalize orthogonally. And then find out that our new axis is in the form x equals qtx, which is the same thing as saying that x equals q times x. And then if you want to find any of the points on your new quadric, all you do is you take the original points on this x quadric and you multiply it by q. So for example, let's go back down here. Oh, my bad. We want to map the x-axis, the 1, 0, 0 axis. We just multiply by q. Map the 0, 1, 0 axis to the q, 0, 1, 0 axis, and map the 0, 0, 1 axis to the q, 0, 0, 1 axis. So that's how we do questions about quadrics. And because we are out of time, we will finish there. But I hope you all learned quite a bit about how to use matrices and how to do some problems in several variable calculus. Yeah, but that's all the time we had for today. Yeah, so do make sure to come to tomorrow's seminar as well, because in tomorrow's seminar I'll just show you a bit of a spoiler alert. We've got some ordinary differential equations, and you'll go through a lot of partial differential equations too, and basically you'll just finish off the entire course. So I hope you all enjoyed that seminar and you found it useful. But yeah, basically, good luck with your exams, and we'll see you again tomorrow, hopefully, for part 2. Okay, so I will have to wait a while just to end the stream, just to make sure that it's complete. All right, thank you guys.